Okay, hello everyone. Today we'd like to talk about the ZKMPC, bringing public auditability into multi-party computation, or MPC. Today I'm excited to share our latest advancement in this field for you. Okay, this is today's outline, but let's start from introduction. And please give me a little bit time to for the team introduction. Also, Yoi Inc. is a Japanese fintech company to help entrepreneurs and businesses to grow increasing asset liquidity with innovative financial solutions. And we are doing R&D for ZKP and MPC to focus on secure and efficient computation. So today I would like to talk about the project which have received 2 ESP grants from the Ethereum Foundation. And this is our team member. This is Yusuke Nakae, a researcher and developer, and I'm Task. And last, he is not here, but we have Masa, co-founder CEO. So let's go into the topic. Let me first introduce about the importance of the secure computation and MPC. So secure computation in data-driven world is really essential. It allows us to protect sensitive information such as healthcare and financial. And it enables useful analysis without exposing information. And multi-party computation, or MPC, is a key technology for this purpose. It enables multiple parties to jointly compute functions while keeping their inputs private. And they only have to share the final results. So this will ensure the secure collaboration. So let's think why the third-party verification for MPC is essential. Especially the case we are using dishonest majority protocols like SPDZ. When we are using dishonest majority protocols, participants like Alice and Bob can verify within themselves that calculation results are computed correctly. However, they cannot directly prove the correctness to the third party, such as Charlie. So in this case, Charlie will think, can I trust this result? That's why adding third-party verification to MPC is very essential. Especially for use cases like application to blockchain, finance, and medical data analytics. So this is the overview for the rest of the presentation. Firstly, we will show how to introduce the public auditability into SPDZ, MPC protocol, by introducing the collaborative zk-snarks. Next, we will secure consistency of the secret input, which enables third party to verify the input constraints using Peterson commitment. And next, we will show our enhancement of the bitwise support for public auditable SPDZ. So SPDZ is well suited for arithmetic operations, but not effective for bitwise operation. So we support functions such kind of comparisons, conditional branching, and bit decomposition, and so on. And this will expand the range of possible applications. And as an application, we implemented the Game Master Free Werewolf, or sometimes called Mafia game, using MPC to showcase how our enhancement will make the MPC more versatile to collaborative use cases. Okay, I'll pass to Yusuke.
Next, to achieve what we introduced, we need to understand the background and issues in more depth, and which we will explain. Firstly, let us begin with the MPC protocol basics. MPC uses the techniques called secret sharing, which is data is split to some shares, and each party has its shares one by one. And there are some kinds of secret sharing, like additive secret sharing and Shamir secret sharing, and so on. Let's consider the example of addition. X and Y is shared, and the addition of X plus Y can be obtained by simply addition of their shares. And however, multiplication and other more complicated operation needs is communication in intermediate steps. Yeah. And SPDZ. SPDZ is one of the well-known MPC protocol proposed in 2011. And this uses additive secret sharing, so it is suitable for arithmetic operation like addition and multiplication and so on. And there are two phases. One is preprocessing, and the other is online phase. And next, we talk about the PA-MPC. Publicly auditable MPC is the most important concept in our session. In ordinary MPC, the correctness of MPC calculation can be verified by participants. However, PA-MPC imposes MPC on or third-party verification. It was proposed in 2014. However, the efficient implementation does not exist at the time. However, in 2021, the collaborative zk-snarks, which is the one of efficient implementation of publicly auditable MPC, was proposed by Özdemir and Bonnet. The idea of collaborative zk-snarks is to prove by multiple provers and recall KZZ commitment. KZZ commitment is a kind of polynomial commitment which is used in zk-snarks, and prover and verifier communicate with each other, and commitment prover compute commitment and send to proof to verifier, and verifier last check that the pairing of specific calculation. And collaborative zk-snarks uses polynomial commitment in ZKP, like Martin and Plonk and so on. And we focus on the mathematical aspects of collaborative zk-snarks. Its idea is very simple. The pi I is a proof generated by shared input, and pi is the total proof. This technique uses the linearity of polynomial commitment, and if we generate the proof each party, then this is a share of total proof. However, if we want to use collaborative ZK or PA-MPC on blockchain, there are some issues to be solved. The figure shows that zk-snarks and MPC additive-oriented and bitwise-oriented MPC. Roughly speaking, we want to develop techniques in this region, which satisfies all three regions. The first issue is the consistency of secret inputs. In SPDZ, there are pre-processing phase and online phase, so we have to ensure that the consistency of secret inputs. And this figure shows that conventional MPC and the publicly auditable MPC. And the second issue is requirement for the general purpose computations. SPDZ-based MPC is suitable for arithmetic operations, however, not suitable for bitwise operations. So we have to implement such bitwise operations, which is efficient for SPDZ. Yeah, and this affects on constraint generation in ZKP because of restriction of finite fields, which can be used in ZKP. And next, we focus on the first challenges, the secure consistency of secret inputs. in MPC, especially in space, the data, input data is generated by using auxiliary data created in pre-processing phase. So we have to be more cautious than users. The committed data, we solve these problems by using commitment. We commit input data before the input shares generated. So and add constraint to DKP, so we can verify that the data in pre-processing and online phase and the proving phase is must be same. And we choose Pedersen commitment to implement. And there are some constraints we implemented, for example, range constraint and so on. And we focus on second challenges, bitwise operation support. Recall why bitwise operation difficult in space. Space uses additive secret sharing, so bit decomposition and comparison, such operation will be more costly than addition and multiplication. So if we're using larger finite fields, then more constraint needs, so we can't, it is difficult to implement bitwise operations. Implementation, we added especially equality zero test and comparison test and bit decomposition on space-based MPC. And we also implemented share conversion protocol because Pedersen commitment needs two different finite fields. And let's look the algorithm detail. This shows the equality zero test. Let's imagine that you have the data X of share of data X, and we want to calculate X is 0 or not. Firstly, we generate the random share R with associated bitwise share, and calculate X plus R and publicize them. This denoted as C. If X is 0, then R and C must be same. So we use this fact and calculate AI, this is bitwise, and output the total amount of all AI. This means 1 if X is 0, and otherwise this means 0. And surprisingly, bitwise operation doesn't need for additional constraint for each party, even if this can be considered as separation of ZKP problems and the MPC problems. So we focus on each regions. And next, we want to show applications and demo video. We developed a werewolf game, game master free werewolf game. This flowchart shows that werewolf game flowchart. Werewolf game is a game. The players are divided into two teams. One is villagers team, and the other is werewolf team. And the player whose role is hidden, and by using specific role action and voting, and player aim to victory for their teams. Usually, a werewolf game is Game master is necessary for werewolf game. However, we developed a game master free werewolf game by our ZKMPC. Here is a list of we implemented the protocol in the ZK werewolf. Role assignment, anonymous voting, werewolf attack, fortune teller check, and victory condition. Such computation is done by MPC, and we can check the correctness of such actions. Let's pick up the role assignment in DK werewolf. Players input the shuffle matrix by secret shares, and then compute the roles by grouping protocol, and they generate corroborative proof of role assignment protocol. Then, if the verification is correct, then they are informed their roles. This is a demo video of our ZKMPC. This is 4 people case. The Alice and Bob and Charlie and Dave. They register name, and then setup began right away. And the role assignment protocol is running, and the proof, here is proof generation by MPC. After the proof generation, the proof is verified, and they are Alice is fortune teller, Bob is werewolf, and Charlie and Dave are villagers. And the night phase, they do special action. Alice fortune teller divined Bob, and Bob attacked to Charlie. And the discussion phase and voting phase is here. Alice and Bob and Dave vote. Then again, the proof generation is started. After the verification of the proof, Dave was executed here. And finally, the victory condition check program is running here, also generating corroborative proof. After creating and verification, game is over, werewolf sides win here. At last, we're looking to the future prospect of our ZKMPC. If it becomes available on blockchain, it can be used as a versatile MPC module on blockchain with smart contracts, and it can be also applied to some regions like machine learning and medical and financial data. Such case where multiple parties need to share data. And the ZKMPC can reduce the security risks and ensure that the correctness of calculation. Thank you for listening.
Thank you once again. Very nice talk. You covered many things. We got an overview of all of MPC, background on different protocols, all that you've implemented, demo, everything, and future. I think it was a really nice talk. Thank you very much. We have some questions. Maybe I will start at the bottom. So maybe I missed it, but which snark did you implement? Growth 16 or something else?
Sorry. I don't write growth 16. However, growth 16 is also implemented for our ZKMPC, like Marlin and Plonk. Yeah.
So Plonk, Marlin, and growth 16.
Yes.
Very nice. Cool. Did you implement everything from scratch, or did you use some existing libraries?
In the part of our program is existing libraries. For example, the cryptographic primitives, we use this ArcWorks library, and the collaborative zk-snark part, we refer to the original work. However, in pre-processing phase of speeds and the bitwise operations, bitwise operation region, we write from scratch.
Nice, impressive, cool. Maybe one last question for me is, where would you be most excited to see this used? What sort of developer or application would you really love to see building this? I think your examples that you did with the games and the demo is super nice, but outside of your team, who would you love to see using it?
Okay. I'm really interested if this is used in kind of medical case or to make the machine learning model together with a different organization. So if each organization has a different secret data and they don't want to reveal the data to each other, but still they can learn the model to create the model, or to also do the estimation from the model. So I'm really excited to combine this technology with machine learning. Yeah.
And you think it's efficient enough to do some machine learning in MPC?
Yes, yes. So if we use MPC in machine learning, the model itself can be private or don't have to be revealed to anyone. Yeah.
Very nice. Cool. Well, that's all the questions we have. We'd like to thank the speakers again for a very nice talk. Thank you.
Thank you.
So, we have a few minutes, 6 minutes before the next and last session.